Hello everyone, my name is Brianne Walsh and I am a science communicator with the UMC's Integration and Application Network. And as Bill mentioned in the first class last Thursday, we are going to be spending the next 2 weeks talking about conceptual diagrams, which are a very effective tool for science communication. And what makes them so effective is that humans are visual creatures. So 90% of the information that's transmitted to the brain is visual, and we only retain about 20% of written text. So we process visuals about 60,000 times faster than text. So to start off talking about conceptual diagrams, we're going to cover what are conceptual diagrams, what makes conceptual diagrams so effective, and then start talking about how we create conceptual diagrams and different ways and types of conceptual diagrams can be used. So just to take a step back and look at the Webster's Dictionary definitions of a concept is something conceived in the mind, and a diagram is a drawing that shows relations. So if we put that together, we have a conceptual diagram, which is a diagram that uses symbols to depict the essential attributes of a system. And conceptual diagrams are effective when they present information clearly and provide context. So this is just a conceptual diagram that I'm sure many of you are familiar with, and it's illustrating plate tectonics, and it's providing context by having that within the Earth's crust. And conceptual diagrams can be used to transform text. So as we said, humans are visual creatures. We are able to retain more information from visuals rather than text. And so by taking 2 pages of text about the cumulative impacts on an ecosystem and turning that into a synthesized visualization, we are not only making that a little more reader-friendly, but also something that someone will retain easier. So here we have the cumulative impacts on an ecosystem, starting with just one impact, which is intensive fishing on the left panel. And as we move through those panels, we are adding pressures into the system, and we can see how that ecosystem is changing. So what makes conceptual diagrams such an effective tool? First, they can help clarify thinking. So this is not only for the person looking at the conceptual diagram, but also for the author that is creating the conceptual diagram. By going through the steps of creating that conceptual diagram, we're starting to clarify our thinking of our own research and the idea that we're trying to synthesize within that conceptual diagram. And then by doing that, they can help aid in communication to the audience. They can also help identify data gaps and management priorities and get you thinking about the key features and threats of the system that you're trying to portray. So as you're creating that conceptual diagram, you might identify data gaps that you're missing or think about management strategies that could be used within that system. So to start off with how to create conceptual diagrams, step 1 is you want to think about and identify your audience. So is this diagram intended for the public? Will it be a group of your scientific peers, or will it be policymakers or managers that may not have that scientific background? And you also want to think about the medium in which you'll be presenting this conceptual diagram. Will it be a PowerPoint presentation? Is it going to be included in a scientific poster or a paper? Or will it just be in a general newsletter or outreach material? And then you want to develop an issue statement for your conceptual diagram. So think about a 1-sentence declarative statement that's summarizing the information you're trying to portray in this diagram. So think about it like an elevator speech where they say you should be able to summarize your research in the 3 minutes that it takes to ride an elevator with someone. You want to be able to summarize this conceptual diagram in 1 sentence. And then prioritize the key features of the system and identify and prioritize the major threats, drivers, or natural resources. So make a list of about 5 to 7 of those features in the system, as well as the threats and the drivers, and try to keep them within 5 to 7 because you want to make sure that you're starting simple but not losing that scientific integrity of this diagram. And then you want to start thinking about and developing a list of symbols that should be in this diagram. So if you're thinking about a certain species that needs to be included, a certain species of fauna or flora, or a certain type of house or a boat that needs to be included, start thinking about that ahead of time. And then choose an ecosystem base and style. So think about the context of your diagram, whether it's just putting it on blue water background or sky, or if it needs to be on a 3-dimensional or 2-dimensional base. So there's three components of a conceptual diagram that we're going to talk about today, and that's a base, symbols, and a legend. So starting off with a base is extremely important in a conceptual diagram, and you always want to start there because you need to provide context for what you're trying to show on your conceptual diagram. And there are lots of choices, whether they're 2D, 3D, or a base map, and think about the processes you're trying to show. Are you going to have to be showing things that are happening underwater in the soil, and choose your base based on those depictions in your diagram. And then we also have symbols. So as Bill mentioned, Ian has created an online symbol library, and we have over 3,000 symbols. And after this presentation, I'm going to ask you to go online and download that symbol library so that you can use those for your own conceptual diagrams. And symbols are great because they are commonly recognizable, so they can transcend cultural or language barriers, and we are exposed to symbols in our daily life whether we know it or not, whether they are mathematics, music, religion, weather, corporate branding, maps, organizations, or even just the road signs on streets. And symbols are information rich, so they can represent something tangible, whether it's a stop sign, a shrimp, a species of bird, or a house, and they can also be used to represent something invisible or intangible. So here we have this symbol of carbon dioxide being absorbed and oxygen being released, and that's how we represent photosynthesis as a symbol. And think about the way that you're using symbols in a diagram with size and color to convey information. So here we have a conceptual diagram of a degraded coral reef system versus a desired coral reef system, and we use the stoplight colors, so red to green, to illustrate good to bad because humans have an innate reaction to the color red and the color green. And then we also use the size of symbols. So here we have sediment loading, which is depicted on the left-hand side as a large brown arrow, and the sediment loading is higher in the degraded system and lower in the desired system, so we've changed the size of the arrow to depict that. We've also changed the color of the water, so in degraded it goes from a brown to blue gradient, whereas in the desired it's a blue color showing that it's cleaner water. And we've also used the number of symbols to depict fish biodiversity and richness. So in the degraded system there's only a few fish and a few species, whereas in the desired system there's high biodiversity and a large number of different fish species. And symbols can also be used in tables. So here we have a best management practice list, and we've used tiny vignettes of symbols and conceptual diagrams to illustrate those best management practices. And on the right-hand side, we have a table of water quality indicators, and each indicator has its own symbol, which can then be carried throughout whatever this document or presentation is. And we've also incorporated those green to red lights, stoplight colors, to illustrate the grades of those indicators. Symbols can also be used in report cards and documents. So here we have the Mississippi River report card scores, and each one of these values for the Mississippi River, recreation, ecosystems, flood control, each has its own corresponding icon that was created using a symbol. And symbols can also be used in data graphs. So here we have projected sea level rise, and we've taken a conceptual diagram and used the bottom of the diagram as the axis, and then we have the y-axis showing year and height, and we've just provided a little bit more context for this data graph. And they can also transform flowcharts. So here we have the different processes occurring within a system, and we've just added a base and a skyline and put in that system, so it makes it just a little bit more appealing than just a box and arrow chart. And you can also use symbols in infographics. So these are each symbols that were just turned into one color icons, and they are showing how Maryland's plan to reduce carbon pollution will impact the state of Maryland. And so the third important piece of a conceptual diagram is a legend, and there's two ways to think about doing a legend. You can either list each of your symbols and what they mean in your diagram with either a couple words or a sentence, or you can use an embedded legend. So on the upper left we have an embedded legend where the author has just taken the caption and inserted each of those symbols. As you read through the caption, you learn what the diagram is representing. And conceptual diagrams provide synthesis, visualization, and context, as I've said before. So here we have a diagram showing sea level rise occurring in the polar regions, and then on the bottom we're looking at the impacts of that sea level rise within Maryland. So you're able to synthesize scientific data of climate change within this diagram, visualize it, and provide context in an area that's recognizable to viewers. And you can create conceptual diagrams in real time with stakeholders and synthesize key messages into a shared vision. So this is an example of a whiteboard, and this was a workshop in Samoa where they were looking at the impacts on an ecosystem from the cloud forest down to the coastal strand to offshore marine. So this was the first cut at identifying the important ecosystems within this system. And then they later decided that this needed to be a three-dimensional diagram to show underwater, and started filling in a legend with scores for each of these systems. And then a science communicator took that drawing of a conceptual diagram and started building a base and building onto that base and adding in that legend, scoring each of those systems. And this was the final product of that conceptual diagram that was included into a newsletter identifying Samoa's unique habitats and cultures from the upland to the offshore marine. So how can conceptual diagrams be used? There's an endless variety of conceptual diagrams and layouts and bases that can be used, and we'll just go through a few right now. And diagrams can be an interface between scientists, community, and the government. So here we have two different conceptual diagrams showing the same area and the differences between pervious surfaces and impervious surfaces. And even if you're just the general public in the community, you can clearly see the differences between these two systems by just adding this best management practice of installing pervious surfaces. They can also illustrate complex processes within a system. So here we have an offshore environment that's experienced nutrient loading. So as the arrow of nitrogen and phosphorus increases and the nutrient inputs, you can see how the system is changing from oligotrophic to hypertrophic. And the author has used the size, used X's to cross out different symbols, and then also added algal symbols at the top to illustrate the increase in phytoplankton blooms. Conceptual diagrams can communicate ecosystem relationships. So here we have the groundwater system in North Kona, Hawaii. So we have the groundwater system that's occurring under the land, and then you can see how that system is then influencing the aquatic resources in the ocean, ponds, and pools. And conceptual diagrams can effectively demonstrate comparisons between different systems or best management practices. Here we have a best management practice of stream bank fencing implied in a system, and we have the cows that cannot access the stream, whereas on the left we have a lack of best management practice. So it's easy to see the differences in the system based on these two BMPs. And conceptual diagrams can also describe processes at different scales. So here we have a mangrove ecosystem, and you can see that process is occurring on the meter scale, so the larger picture in this mangrove ecosystem. And then we've used these circle blowouts to describe processes happening at a microscopic or on the scale of centimeter in the ecosystem. You can incorporate conceptual diagrams into photographs and maps, and here is a photograph of the coastal bays of Maryland looking into Ocean City, and someone has just used a conceptual diagram on the bottom of this photo and drawn what is happening underneath the water in the bays. So diagrams are excellent resource management tools. You can illustrate healthy and productive systems compared to degraded and unproductive, and look and see how ecosystems are at a tipping point and what those look like. You can also use diagrams to educate the public. So this is a very simple diagram showing the difference between a living shoreline as compared to a hardened shoreline in a system, and it's really easy to see the differences even without a legend for these two diagrams. And you can also use diagrams to explain best management practices, as we've seen before. So these are just little vignettes of best management practices that have been employed throughout the Chesapeake Bay watershed, and we're just highlighting each of these best management practices in these diagrams. You can also use diagrams to explain monitoring and data collection. So here we have a watershed, and there are 4 different types of data collection being used, and we've used these little blowouts to illustrate each of those. And you can use diagrams in scientific publications, in journals. A lot of journals now are accepting color images. You can use them in posters, reports, books, presentations, and it's really important to create a portfolio of great scientific graphics and visualizations that you can reuse over and over again. So just to wrap up, conceptual diagrams allow stakeholders to be engaged and allow a shared vision to be created for a system. And you can use conceptual diagrams to identify gaps and priorities within a system and show complex scientific concepts and synthesize them into information-rich database visualizations. So you're simplifying systems but not losing that scientific integrity. And science is effectively communicated to a wide range of audiences through science visualizations. So just to kind of get into creating conceptual diagrams, there's a few steps that I want to go through that you can start thinking about before class on Thursday. So first you want to start thinking about your audience and your base and the symbols, and we have a tool that can help you that has been uploaded to Moodle, and it's a guide for creating conceptual diagrams. So this will run you through identifying your audience, thinking about your statement, prioritizing key features, and starting to think about the base and symbols for your diagram. And so we've uploaded this, and there's black text to describe each of these steps, and then we have an example that's been gone through in a series of diagrams for Lake Tahoe. So the second thing you want to do is start simple. So get out your paper and colored pencils. You don't want to start with the software. It can be too overwhelming. And every time that we create a conceptual diagram, we start simple. We start with a pad of paper, and I am not a trained artist. I do not make masterpiece conceptual diagrams when I draw them out. I sketch them out and make sure I have all the symbols that I need on there, and I have my base correct before I even get to the computer. So here we have a diagram of a coastal lagoon system, so looking at a closed lagoon versus an open lagoon, and then someone, after sketching, moved to the software and started creating the diagram. And you also want to be sure to solicit feedback from colleagues and collaborators on your conceptual diagrams. Because we are visual creatures, it is important to get feedback from other people because people see things and think about things differently. So always make sure that you're getting feedback on your conceptual diagram. So this is an example of a diagram of the coastal bays of Maryland and Assateague Island, and this was after a first review, and then it was updated again after a second round of reviews, and this was the final conceptual diagram that was created. So just to summarize for this week, here's my contact information in case you have any questions or need any additional information. And for Thursday's class, there are a few documents that have been uploaded to the Moodle site. One is a conceptual diagram newsletter, which just summarizes some of the concepts that this presentation has talked about. So if you could review that diagram newsletter, that would be great. And then work through the creating a conceptual diagram worksheet and start creating and drawing out your own conceptual diagram on a sheet of 8.5 by 11 paper, computer paper, however you want to do it. And try to install that Ian symbol library and swatches onto your computer and into Illustrator. So if you have any questions about that, I've put instructions online, and there are also instructions on the ian.umcs.edu website. So I will see everyone on Thursday.